Hi there everybody, welcome to another lecture for the MCAT ACE series, and in today's lecture under the general chemistry topic we are going to be covering chemical and enzyme kinetics. Now I will mention when we get to enzyme kinetics we're talking a little bit more about the biochem realm, but you can still fit the general idea of kinetics into general chemistry and understanding rates of reactions, whether it's enzyme substrate complex or whether it's reactants products. All of this falls into rates of reactions, which we refer to as the kinetics. So, what are we going to cover in today's lecture? Well, the first thing we will discuss is basic reaction kinetics. So, if I have some compound A that's going to be turned into some compound B, how can I analyze that reaction in terms of concentrations of reactants and products and relate that to how fast the reaction is going to occur, or the kinetics of the reaction? So we'll take a look at this in respects to time and also concentration, whether something is increasing or decreasing. And in a forward reaction, we would expect that the reactant concentration would decrease and the product concentration would increase. And of course, we have the concept of reversible reactions where the opposite could be true, and equilibrium where we're batting it back and forth. Then we're going to take a look at rate laws. Rate laws are very important. They play into kinetics. They're pretty much what defines kinetics. So we need to discuss rate constant, which is that K that we normally find when we are discussing any type of chemical kinetics equation. And then we need to discuss order of reactants in the reaction. Now when we say order here, we're not talking about order as in placing the reactants in a certain order. We're talking about the order or the exponential order to which the concentration of these reactants will affect a reaction. So you may remember there can be things such as zeroth order, first order, second order. So for instance, if a given reactant is considered second order with respect to the reaction, that reactant is going to be squared when we look at its concentration as far as how it would affect the rate and the rate law. So we're going to take a look at that both for individual reactants and then the reaction order overall. So there's an overall order to your reaction, which is really just the sum of all the orders that the reaction contains for each individual reactant. We'll take a look at determining rate laws. This is typically done experimentally, but you can certainly come across problems like this where they'll say, you know, concentration of B is held constant and A is manipulated. Here's what happens to the rate. And then we do the same thing where we manipulate B and we hold A constant, and then you take a look at how each of those will affect the rate law. So you can use that in things like determining your rate constant, and you can certainly use it to determine the order of your reactant concentrations. Then we will take a look at predicting concentrations with respect to time. So when we look at these, there's a natural decay of reactants that you want to look at. And there's some equations we'll bring up that use natural logarithms and things like that, depending on whether you're talking about a first or a second order concentration. And then we will discuss also the concept of half-life, which is a time-dependent reaction. Right after a certain amount of time, half of the concentration is gone, and then that same amount of time it will take for another half of the concentration to be gone. So then you're down to a fourth, and so on and so forth as you continue going that way. We will take a look at temperature and activation energy. So this is known as the Arrhenius equation. We'll take a look at how a catalyst can play and affect this. And then finally, we will take a look at enzyme kinetics. So for those of you that have had biochem and know about enzyme kinetics, we're talking about Michaelis-Menten, we're talking about Km, we're talking about Kcat, the binding of the enzyme substrate complex, the dissociation of that complex versus the moving forward and the product, which tends to be assumed as an irreversible reaction. And part of the assumption, as I just stated, you assume, is looking at steady state assumption or steady state kinetics. And so we'll take a look at what is involved in all of that. So let's go ahead and get started here. The first thing we're going to talk about is just basic reaction kinetics when we're looking at a given reaction. So that's the first thing we're going to do. So if we move down here, let's take a look at general rates for chemical reactions. And we're going to keep this very simple as we're starting out, because there will be plenty of examples where we do the math and the more complex stuff as we're moving along here. So for a general rate, let's take a reaction where we just say some compound A is going to decay into or turn into some compound B, right, through a chemical reaction process. So there are two ways that we can really observe the rate that is occurring here. So the first way that we could observe the rate is we could say the rate is going to be equal to negative delta bracket A over delta T. All right, so what does this mean? The negative means the disappearance of, because we're expecting, if this is a forward reaction, that over time A is going to lessen. So the concentration, we would expect a decrease of A with respect to time as this reaction moves forward until we have no A and it's all been converted to B, or we have very little of it left. All right, so that's one way that we can measure this. Now, the delta, that triangle, means change in. So we're looking at the negative change in concentration of A, that is to say the disappearance or the decrease of A with respect to change in time. So that is one way that we can look at the kinetics of this reaction. Now, what about for B? Because B is forming, so it's going to be similar, but it does have some difference. So, or, when we get ready to take a look at B, we can say that the rate of this reaction is going to be equal to the change in concentration of B with respect to time. Now, what's the big difference here? There is no negative sign, right? So this is really positive change in B, and that's because B should begin to increase if this is a forward reaction as the time changes. So with change in time, we're expecting the concentration of B to continue piling up. And so this does not have the negative. You usually won't see this with a plus here. I'm writing it for the purpose of this discussion, but it's an implied positive change in B when you don't have that negative sign there. All right, now if we take a look at this unit, concentration is typically given in molarity. You could find other units that you can work with for concentration, but molarity is the most common in chemistry. And then at the bottom is change in time, so that's seconds. So the unit that we would be using is molarity seconds. All right, so the concentration, or really the change in concentration in respect to the change in time, molarity second. So just keep that in mind as we're discussing this. This does have a unit that is associated with it. All right, so that's the beginning there. Now, what if my reaction is slightly more complicated? Well, if I have A plus B equals C plus D, we could still turn around and say the rate is equal to negative change in A over change in time, negative change in B over change in time, positive C time, and then positive D time. So just adding additional reactants and products is simply giving us other opportunities to write the rate equation depending on how we would like to view it. So that's not horribly complicated. But what happens if it's not a one-to-one ratio? Because up here we say 1A is going to convert or lead to 1B. And then what happens if we have a reaction where we say, well, it's not one-to-one, it's really that 2A is going to yield 1B, right? So what happens if I have 2 of compound A and that goes over to B? So in that case, we're going to need to take a look at this rate with stoichiometric ratios in place. And so when we do this, we need to consider that for every 2A that decays, right? So for every 2A that decay, or decrease, or whatever you want to call it, because decay, sometimes people associate that with radioactive. But for every 2A, you're going to get a positive 1B, right? So the ratio is not exactly the same there as a one-to-one. So what we would need to say here is that the rate is going to be equal to negative 1/2 the disappearance of A with respect to time. All right, or we can say the appearance or the change in concentration of B with respect to time. So why is this negative 1/2, whereas before it was just negative? Because if we take a look at it, the ratio here is 2-to-1 when we're looking at A to B. So another way that you could state this is that B is going to form at half the rate at which A will disappear. Right? So if A is going to disappear at 2 times that, then B will form at half the rate. All right? So if we're relating these, because it says or means equals, so if we're going to relate these two, if we're saying that B forms at half the rate at which A disappears, then we can relate these two this way. All right, so that's an example where you would have to use your stoichiometrics. Now, what if A was 4? Then it would be -1/4 when we're looking at something like that. All right, so just keep that in mind. So let's frame this relative to an actual reaction that we're interested in. So let's say that you come across a question on the MCAT that looks like this. You have 3 moles of molecular oxygen, and that is going to yield 2 moles of ozone gas, right? So this is a similar A to B type of scenario that we've been showing above, keeping it consistent. So how would I express the rate in relation to this, right? What if they gave you a bunch of options? Which one would you pick? So if you were to analyze this, you would need to say that the rate here, all right, let's use colors to identify each one. So first, let's, as we've been doing, relate this to the reactants. So for purple, we'll do O2. So the rate is going to be equal to -1/3, because it's a 3:2 ratio, of the concentration of molecular oxygen disappearance in respect to time. And that is going to equal, or, right, so this is where we're saying or, we could state it this way, 1/2, that's a positive because we're expecting the appearance, right? Change in concentration of ozone appearance relative to change in time. So you could express either of these here, right? So you have the O2 and you also have the O3. This is how you could relate them to one another as far as the rate disappearance and the rate appearance. That's what we're looking for. All right, so the next thing, now that we have a general understanding or a basic idea of reactions kinetics in relation to time and concentration, we're going to take a look at rate laws. So let me just clear the board here, and then we will get started with rate laws. Okay, so here is the information for rate constants and orders when we're dealing with these reactants. And we're going to go through, we're going to start doing some math here. So I would suggest that you have probably a pen and piece of paper as you're going through this so you can take notes on it. And certainly a calculator would be a wise idea, some sort of a scientific calculator as we're going through this. Now, let's discuss rate constant, and then we will get into orders. And this is referred to as rate law. So when we are creating a rate equation, and we're actually going to start putting in and plugging in the concentration values, you are creating a rate law for a given reaction. So any reaction will have a rate law that is associated with it, and within that rate law is a rate constant, which tells us pretty much how quickly the concentration or the concentrations, if you have more than one, are going to be decaying in that reaction. So when we do this, we want to base our reaction on initial rates and initial concentrations. Now, some students ask why we do this, and there's two main reasons for this. Number one, it's going to avoid small concentrations of reactants. Now, if you're doing this outside of the lab, that may not seem that critical to you. However, if you are in the lab, in order to determine your concentrations, you need to be able to measure those concentrations. And as concentrations get infinitesimally small as the reaction moves along, it can become very difficult to detect or to pick up concentrations as they get smaller and smaller. So if you base it off of your initial concentrations, that is going to be easy because I know I can make up these solutions, or I can use these gases at a starting concentration. I know the concentration. I know how many moles of each are in the solution when I first start the reaction at some initial time. Usually, in a lab setting, that is going to be time 0. Now, we'll see as we go further into this, we don't always have to base something on time 0. But when we do rate constants and you are trying to experimentally determine a rate law, time 0 is usually the best point because you know the initial concentrations without a doubt. You know exactly how much of each you've put into the solution to start the reaction off before it's off and running. Now, number 2. This also avoids any issues with reversible reactions. So we mentioned this earlier. Reversible reactions will not always be present, but it is very possible that you can get an equilibrium set up where you have some forward and some backward movement. And when you have reversibility in your reaction, that is a separate rate of products going over to reactants, and then you have two different rate laws that are kind of intermingling or competing with one another, and that can screw up your initial rate if you don't account for it. So if we go at the beginning of the reaction and it's just reactants that we've dumped into the flask fresh and we're starting it, there is no product that's been formed. So it eliminates the possibility of reversible reactions occurring at time 0 or at some initial small amount of time chunk that we're looking at. Those will tend to happen as the reaction proceeds further and further on. All right. So that is the reason we always like to base this. It's a little bit of theory, but that's the reason we always want to base our determination of a rate law for these reactions on initial concentrations and initial rates that we find. So let's take a look at an example with a reaction where we can determine this. So I have an example here. We have fluorine gas, and we're going to react that with chlorine dioxide. Now I'm going to give you the balanced equation here. You would, if you were handed this, need a balanced equation. It's going to be important if you were to be asked anything related to stoichiometric ratios and things like that. So this is going to produce 2-chloral fluoride, and that is FClO2 gas. All right, so this is the reaction that we have. Now, the way that this is determined experimentally is you run through trials. And I know I was mentioning this earlier, so we'll do 3 trials here. Trial 1, Trial 2, and Trial 3. And the idea is that we're going to hold one of the concentrations constant while we change the other, and we will take a look at the rate and how it is affected. So for fluorine, the 3 trials, we're going to set the values equal to this. So it'll be 0.1 molarity for the first one, and then we'll hold that constant in Trial 2. All right, so we have the same exact amount. And then in Trial 3, we're going to manipulate the fluorine, and we're going to double the concentration of it so that we find this. Right? So then, if we come over here, we've got the chlorine dioxide. With the chlorine dioxide, we're going to do the following. We will use a 0.01 molarity in Trial 1. In Trial 2, because we're holding the fluorine constant for the first 2 trials, we're going to manipulate the chlorine dioxide here. And the value we're going to use here, let's say that we quadruple the concentration, so by 4. And then we would want to obviously hold it constant in this last one in comparison to reaction 1, because the idea is if you look at Trial 1 and 3, we want to manipulate the fluorine and hold the chlorine dioxide constant in that case. So that way, if I take a look at the rates that come out of this, right, this forward reaction, so here's the rate as we're producing the chloral fluoride. As we're doing that, we want to take a look at how each manipulation would affect it. So the numbers that I'm going to use here, we've got 1.2 times 10 to the negative third. So that's the rate when we use the first set of concentrations. Okay. If we do the second set where we multiply the chlorine dioxide by 4, it turns out that the rate is approximately 4.8 times 10 to the minus third molarity second. And then when we go to Trial 3, it is going to be 2.4 times 10 to the minus third molarity per second. So those are the rates that we have here. Now, how do we analyze this and how do we use it? Well, what you're going to want to look at is what happens to each rate with respect to each reactant. So the first thing we manipulated was the chlorine dioxide. So we saw here that when we have ClO2 and we multiply it by 4 as far as the concentration, right? So if the concentration is multiplied by 4, we go from 1.2 times 10 to the negative third to 4.8 times 10 to the negative third. So what happens to the rate in that case? The rate is also going to increase fourfold. If you do the math on that, if you were to look at that, 1.2 times 10 to the negative third times 4 is 4.8 times 10 to the negative third. So that is a quadruple in rate for a quadruple in concentration. So we can see that the rate is staying proportional to the concentration of the chlorine dioxide. If I increase it, the rate's increasing. And at this point, we would make a safe assumption to say if I decrease it, it would also decrease the rate based on that dependence that we're seeing there. All right, so then the next question is, what about the fluorine? So that's for trials 1 and 3. And if I look at the concentration of the fluorine, in this case, it was times 2, right? Because we went from 0.1 to 0.2. And so if I take a look at the rate, it went from 1.2 times 10 to the third to 2.4 times 10 to the third. So the rate, once again, shows a proportional type of behavior relative to this fluorine. So how can I write this or express this? I have the concentrations, right? So what I can say is the rate is going to be equal to, all right, now the question is, what do I do? Well, it's proportional to, right, the ClO2 and the F2. That's what the rate is proportional to. So if I say proportional, that means that as the concentrations of both of these decrease, I'm going to see a decrease in the rate. That's what makes sense, because as I saw the increase in concentrations, I saw a jump in the rate. So what's going to happen is if I take some initial set of concentrations and they start moving over to products, I'm losing the concentration of my initial reactants. I expect the rate to continue to go down. So it's a change, the rate is changing over time, right? That goes back to the beginning part. We said delta T in our equations. And the reason we use that background was to prepare us for here. If we have delta T and time is changing, the rate can also change as the time changes. So what I'm going to need to do is I'm going to need some sort of constant, which we represent by K when we're dealing with chemical kinetics. And this is the rate constant. So what we can say is that the rate will be equal to the concentrations of these reactants as long as they are multiplied by some rate constant K. And the rate constant is in there in order to help us keep track of what's going to happen as we have a decrease in the time and the concentrations. And that is what we will use it for. So I can solve for my rate constant by algebraically rearranging this. So if I wanted to algebraically rearrange it, the only thing that I would need to do is solve for K, the rate constant. So I would say that K is going to be equal to the rate, and then I would divide through by each of my reactants to get them away from K. So it's going to be rate over the concentration of the chlorine dioxide times the concentration of the fluorine gas. So once I have this, all I would need to do is go up and use the values that I find for any of the trials. So we'll do trial 1. We're going to select, let's use a color here just so you can follow along. All right, we're going to select trial 1. So it's going to be 0.1 molarity of the fluorine gas, 0.01 molarity of the chlorine dioxide, and the rate is going to be 1.2 times 10 to the negative third. So if I bring that down here and I plug it in, then K is going to be equal to 1.2 times 10 to the negative third. And keep in mind the rate unit is meters second, meters per second, molarity per second. And then if you have the concentrations here, we said that it was going to be 0.010 molarity for the ClO2, and then the F2 is going to be 0.1 molarity. All right, now if you take a look at this, one of the molarities will cancel with the other, and so the unit that you would come out with is going to be molarity second, and that would be for your rate constant. Now this turns out to be the unit for a second order reaction, and we're about to talk about orders in a minute. You may get a different unit if you only had one molarity down here instead of two, right? So then it would just be per second. So if I solve for this, it turns out that the rate constant is going to be equal to 1.2 molarity seconds. Now notice that you have the division there because the unit is really 1.2, and then here's your unit, 1 over molarity second, like that. All right, so this would be the rate constant. This would be the value of K in the case of the reaction that we utilized up above there. So that is how you can experimentally determine your rate constant. Now, how about if we wanted to determine the order of the reactants themselves? So if I take a look at rewriting my rate equation, I can say that rate is going to be equal to K, and I'm going to express it in a different way. So K can be A with a small a up here, and then it can be B with a small b up here. All right, now A and B, when we're talking about the small a and the small b, are going to be the order associated with the concentrations, with the reactants here. Now, you can determine the order based on the experimental evidence that you have. So all you need to do is look at the change when you were to affect either of these concentrations, and that should give you the information about the order that you have. So if I go up, we already determined this, we just weren't aware we were looking at order at that time, right? So if I look at the change in concentration when I go from 1 to 4 times, or fourfold in its change for the ClO2, I saw a fourfold change in the rate. So what does that mean? Well, if I divide rate 1 and rate 2, I'm going to get what value? And the answer you should come up with is 4, right? Now, if the concentration changed by 4 when I'm doing that, that means that the overall order is going to be first order. So what do I mean by this? Well, I mean if we had some initial rate and the answer here was by 1, right? The B was held constant, so I'm not going to focus on that. And then I did it again, and I examined a 4 times concentration increase, and the rate here was 1, and then the rate here was 4, right? Those are the relative ratios to one another. Then that means that the exponent here must be 1 in order for this to hold true, right? Because if, let's say, the exponent was 2, so that this was squared, then I would be taking 4 squared, okay, which would not equal 4 in that case. Then I'd be talking about 16. So you have to look at the math associated with, if I do something to my concentration, what is going to be the change of the rate? And I'm looking at the proportionality or the exponential increase if it's more than a first order change that occurs there. So you probably can tell by the data that's here that when we do it with fluorine, we get the same exact thing. So I can rewrite this rate law by saying that the rate of the reaction I was examining is equal to its rate constant, which we already determined, times the concentration of chlorine dioxide raised to the first power, times the concentration of fluorine raised to the first power, because both of these are going to stay exactly proportional in how they affect the rate. So when I have this, there's a few things that I can state here. I can state that the reaction in relation to ClO2 is going to be first order, and that is based on the exponent that I find there. The first order comes from this 1 here. So then I can also state that the reaction with respects to fluorine gas is going to be first order. The reaction overall, so the overall reaction, is going to be considered second order. And that comes simply from adding up all of the orders. So if I had first order plus first order, then that means the reaction is going to be second order overall. It's first order with respect to chlorine dioxide, it is first order with respect to fluorine, and then overall it is considered second order when I sum those together. So that is how you determine order when you're looking at the math. And you can find rate constant and order if you have that experimental data, and then you can start solving for rates of reactions based on that. That's how a lot of kinetics work is done when we want to determine the rate of a given reaction. If we've discovered a new one, we have to have a way of monitoring the progress of the reaction, and we need to know the concentrations. So that takes care of talking about rate laws, rate constants, and the order of reactants and reaction. So now we've really determined rate laws. I kind of built that in as we were going through it. So you saw as I went through there, the rate law, right? We determined the rate constant, we determined the rate order. This right here was a fully determined rate law. That is a rate law right there. You've got the rate constant, we know what its value is, we solve for it. We also have the orders, and all I have to do is plug in concentrations, and I would be able to determine the rate at any given set of concentrations for that reaction. That's a rate law. It's the law that governs how fast the reaction is going to go. So we have accomplished that. The next thing we were going to take a look at is predicting concentrations over time. So keep in mind, we sort of kicked off this idea of rate laws, rate constant, saying we're going to go for the initial concentration at time 0. And then I kind of mentioned in there, it doesn't always have to be time 0. You can look at it in relation to any given point in time, and that's what we're going to take a look at next. So we'll look at time in relation to the order of a given reaction or an order of a specific reactant, and then we will take a look at the idea of half-life, and that becomes very important, especially in the medical field when we talk about drugs and their half-life. If we have to give them and they could potentially have side effects or things like that, right? We need to determine how often you can take something. That could be based on half-life and how quickly it's breaking down. And then we will continue the rest of this. So let me clear the board, and then we will get ready to talk about the predicting concentrations with change in time. So I will be right back with that. Okay, so what we're going to discuss now is change in concentration for any given reactant that we want to look at in relation to time. So remember when we started this, we said delta T, and we kept saying time could change, the concentrations change relative to time. We had that set up where we said basically delta concentration of reactant over delta time. So we were saying that those two would play off of one another in relation to the rate. So that's what we'll take a look at now. We want to examine this relative to first and to second order reactions because they're going to be a little bit different in how we calculate them. So for a first order reaction, you can relate concentration to time through the following mathematical equation. And that equation is ln, which is the natural logarithm of concentration for A, which is any reactant A, this could be a B or a C or anything else, at a given time t in comparison to or over that same concentration of A at some initial point. All right, so let's just keep track of this so we understand here, because the math can get a little complicated. A naught, or the concentration of A, and let me put that naught outside. Okay, so the concentration of A naught is going to be at some initial time. And then when we look at the concentration of A t, or A sub t, it's going to be at some time t, right? So some amount of time has passed versus the initial time. Now, it's important to note that A naught does not need to be time equals 0. So remember, this is where I was saying at the last portion we were working with, we're going to work with time 0. We're going to start with the initial rates and the initial concentrations. sometimes you can do that. You are welcome to use times 0 here, but it doesn't mean you have to have times 0. You can say, I would like to know at time 5 minutes, seconds, whatever it is, in comparison to time 7. So let's say from 5 minutes to 7 minutes, I want to see the difference in concentration. You can do that. So time initial can be any starting point in time as long as you've progressed to a further point in time, which is time t. All right, so we're going to take the natural logarithm of those ratios, and we will set that equal to, okay, what we would always need is the rate constant, which is going to have a relationship of negative k, that k is rate constant, times time. So here you go. You can relate time that has passed to concentration differences through this equation. This is for a first order reaction that we can utilize this. Now you can rearrange this, and it's useful if you do. You have to use a little bit of differential equations, but I'm going to rearrange it for you here. You've got ln a t equals negative k times t plus ln of a naught. All right, so that's some differential equations with natural logarithms. Now when you do this, if you identify it, and some people may have picked up on this, you have y m x plus b. And this is the equation for a slope, right? A linear equation for a line or a slope that we would use. So why is this useful? Because I can then create a graph if I have some data for these values, and that graph, if I have an equation that relates this, I can find the concentration at any given time, provided I know the x, the amount of time that's elapsed from the initial time. So this is very useful for us. The way that you would look at this is you've got some initial concentration. It's going to decrease as time goes on. And as far as the axes are concerned, t is your x here, right? So there's x, we're identifying that as t. And then the y, so the independent variable, is going to be along here, and that is going to be ln a at time t. So we can find the concentration of given reactant A at any time t if I can relate this through an equation. So where are the other pieces here? This part right at the start here, that is the ln of A at initial time, right? So this, if you were to look and say, here is time, well, at the initial time, whatever it might be, it doesn't have to be 0, but we can say at time 0, that's the concentration at time 0. That's what we've got right there. And then I can look at how that concentration changes or decreases over a given amount of time. And then the slope here, based on it, would be our m, so that would be the negative k. So the negative rate constant would be the slope of that line. And there you go. You can interrelate all of them. That's a very useful equation to use if you want to monitor concentration with respect to time or make a prediction like that. So what about some of the math if we were to implement this? Well, let's say that I had, using this type of graph or this type of data, let's say that at some initial time, doesn't matter what it is right now, I have a concentration of 0.25 molarity, right? And then let's say after some amount of time has elapsed, that concentration is 0.15 molarity. It should be going down if my reactant is being consumed. Now the other thing I would need to know here is I would have had to experimentally examine and determine the rate constant. So in this example, we're going to say 6.7 times 10 to the negative fourth, and the unit here is going to be per second, and that is because it's first order. So second order is going to have the molarity second, which is what we saw in the previous part of this lecture. Because this is a first order reaction, not a second order reaction overall, it's going to have a different unit there. So how would I solve the amount of time that it's going to take for this to occur? So in other words, how long is it going to take in time, and the time would be seconds based on the unit here. How many seconds is it going to take from some initial point where my concentration is 0.25 molarity for it to finally reach 0.15 molarity? The rate constant is what's going to tell us that in this equation. So what I would do is I can come back up and use the equation that I have right here in order to solve for this. Now if I had a graph, I could try to go in, or I could plug in the values. So what we'll do here is we'll solve for this by saying the natural logarithm, again I would suggest a calculator at this point unless you do natural logarithms in your head. The natural logarithm of 0.15 molarity over 0.25 molarity. Okay, now why is this the case? Well, look at the initial equation. It's AT, so the concentration at your final time, over the initial. The final concentration at some time t is 0.15, and the initial concentration at some initial point was 0.25. That's why I have it in that order there. Is going to equal, and if I go back up and I take a look, it's negative k times t. So negative k is going to be negative 6.7 times 10 to the negative 4th per second t. And now all I need to do is solve for t. So what you should do is take the natural logarithm of this ratio in your calculator, then algebraically solve for the rest of this and see if you can come up with t. So pause the video here for a second, see if you can come up with t, and then unpause it. Alright, so hopefully what you got was approximately 7.6 times 10 to the second seconds. That should be the time that it takes for 0.25 molarity of whatever A is to turn into 0.15 molarity of whatever A is. So this is approximately, if you were to convert it using minutes, this is approximately 13 minutes based on the rate law of this reaction. That is how long it's going to take for this amount of concentration decrease for whatever the reaction A is involved with. That's how we're utilizing this reaction and this specific equation. So the next thing we want to do is, if this is for the first order, how do we deal with the second order? The second order is going to have a slightly different equation, so let me clear the board here and we'll look at second order, and then I will briefly mention half-life and what you need to do if you wanted to find a half-life. Alright, so if we wanted to do in relation to a second order reaction, and we wanted the same sort of predictability power, the equation turns out to be this. It's going to be 1 over the concentration of A at a given time t, and we will set that equal to 1 over concentration of A at some initial time, A naught, plus KT. So this is the equation that you will use if you wanted to do a second order. Now what does this look like? It's going to look a little different, and some students get confused by this at first, but remember that we're dealing with 1 over AT and 1 over A naught. Okay, so when we see this, you're actually going to have a slope that's climbing up in this direction if you were to graph this particular one. And when we do this, what you're going to find is you'll still have t down here. Up here you're going to have 1 over A at time t. So if you were to use, let's say, a linear equation here and you were to find out what that concentration is, you would need to then flip it, because what you have is the reciprocal or the inverse at that case. Now, if the starting point is down here, then this is where we're going to find the 1 over, remember last time it was at the top, so 1 over A naught would be down there, because it's 1 over, it's not just A naught in this case. And then if we were to come here, this one right here is going to be your slope, and the slope is just equal to k in this case, whereas last time it was negative k. This time it's just going to be k based on the equation that we have there. Alright, so This would be for second order. You would perform similar algebraic math if you wanted to find any of the concentrations. Okay, for the sake of time, we're not going to go through an additional one like that because we still need to get to enzyme kinetics and talk about half-life briefly. So for half-life, all you need to do, whether it is a first or second order reaction, is you need to consider that your half-life is the amount of time that it takes for half of the initial concentration to disappear. Right? So the half-life, let's say that I have something at a concentration of 1 molarity. The question is, how long is it going to take to get to 0.5 molarity? That would be a half-life, right? And then the question is, with that, how long is it going to take if I use T half again? And it should be the same amount of time as you're working with that. Okay? Then you're going to have 0.25 molarity, and so on and so forth. So it's going to continue to cut it down into smaller and smaller portions by half each time. And what you need to consider if you wanted to solve for half-life using the equations we've shown is that AT should equal what relative to A naught? See if you can think of it for a second. Okay, so the concentration of A at a given time T, if we're trying to frame this as far as half-life is concerned, is going to need to equal A naught divided by 2, right? Because if half-life is half of the concentration is left, and then half of that initial concentration is left, and half of that initial, so on and so forth, then at every time you're looking at AT should be half of what the initial A was. So if A was 1 molarity, like we set up there, okay, 1.0 divided by 2 is going to make it 0.5 molarity. And so half-life is related by plugging this value in for your AT. So if I were to go back through any of these equations, right, I can plug in the A naught divided by 2 in place of AT. So for instance here, I could put in A naught divided by 2, and then just keep A naught over here. That would solve for this specifically at a half-life. You could also, if you had graph versions of this, like we were sort of hand drawing out there, you could determine half-life if you took some initial concentration on the graph and then saw how long it took for it to be half of that given concentration. So the difference in T there, if I go from time 1 to time 2, however much time has elapsed, that would be the half-life of that specific reaction. Okay? This is, in general, when we're talking about this, we're talking about if you have a linear decay of whatever's going on. Sometimes maybe you have a reaction that speeds up as it's going along due to biological factors, so you could maybe get an exponential decay or something like that where the half-life could be changing, but that goes a bit above and beyond what we're talking about here. So that is half-life. What we really want to move on to now is we're going to talk about temperature and activation energy, relating that to the Arrhenius equation and what is a catalyst going to do. And then we will talk about enzyme kinetics, especially after we talk about catalysts, because that's what an enzyme essentially is. It's going to be a biological catalyst that's going to get certain reactions moving along. So let me clear the board here, and then we will move over to temperature and activation energy, and then finally wrap up with the enzyme kinetics. Okay, so what I've brought up on the whiteboard here is we are now going to talk about temperature and catalysts and how those can affect the rate. So far we've been looking at rate laws in relation to the rate constant K and the varying concentrations of any reactants that would be participating in a reaction. So some of the other common things that can affect your rate is temperature and catalysts. So we want to take a look at how these are going to play into the rate law, and it's specifically going to affect the rate constant that we'll relate through the Arrhenius equation in a couple of minutes. It's also important to understand the concept of a catalyst, because when we get to the biochemistry portion, which is what we're going to be talking about next with enzymes, enzymes are really a biochemical catalyst in the body that's working with a substrate in order to turn over and produce product or whatever the desired compound is. So what we're going to take a look at now is a general idea of how temperature is going to increase the rate of a reaction. So if you think about this, this really has to do with collisions. So when we're dealing with molecules, we can associate that molecules are moving around in solution, and the way that the molecules are going to react is that they have to collide with one another. And it turns out they're going to have to collide with one another with enough kinetic energy in order to overcome what's called the energy of activation for that reaction. So how does temperature affect this? Well, as we increase temperature, we're going to increase the kinetic energy. So as we are heating the solution up, or the reaction that we have of interest, the molecules are going to move faster and faster in solution as we turn that heat up. So we are increasing the kinetic energy through temperature of those molecules that are moving around in solution. Now, if we increase the kinetic energy, that is also going to increase their movement, which is going to increase the number of collisions. So the collision rate is going to go up as we turn up the speed on these molecules and we provide them with more kinetic energy. So what's going to happen if we have an increased number of collisions? That is going to lead to an increase in rate. So that is how, when we look at temperature, temperature can directly affect rate based on the kinetic energy and the collisions that are occurring in solution. Now, we already said that if we have a reactant at some concentration, provided that it's not zeroth order, meaning that when we have some sort of a exponential multiplier up here, it's going to have an effect on the rate. If we increase the amount of concentration, we're going to increase the number of collisions as well, because we are placing more and more reactant into the solution, so the statistical probability of collisions occurring is going to increase the more that we populate the reaction with that given reactant of interest. So that's how this is really working. Now keep in mind, as I said a moment ago, the kinetic energy here, just because the molecules collide, does not guarantee a reaction. So the kinetic energy and the force with which these molecules collide is going to have to be greater than or at least equal to the energy of activation for that reaction. So that is usually denoted as a large E and then a sub A like that. So if you take a look at an energy diagram for a reaction typically looks like this. Now I'm going to draw a simplistic one. You have some starting point, you go up through a transition state, which is also called an activated complex, and then you drop off at your product somewhere. So if this is the reactant, this is the products, and then this right here would be sort of a complex, an activated complex where your reactants have met one another, right? So let's say that A has collided with B, and they are in the process of converting over to some product C. That is the high energy point. As they've collided, there's the most energy at that point in the reaction. So the energy of activation is going to be from the reactants, because the reactants would have a certain amount of free energy available to them, and then that is going to be between the reactants and the transition state up here, the activated complex. A lot of students think that it's the reactants to the products, and that is not correct. That's the change in energy from the reaction if you've gone from start to finish. All right, so over here we would have energy on this axis, and then down here it's often called the reaction coordinates or reaction progress. So this is the lifetime of the reaction as it's occurring, and you're watching what's happening to the energy over the lifetime of the reaction. So this part right here, again, this little hump, is what we're trying to overcome when we have that kinetic collision. So how does a catalyst affect this? We can understand the number of collisions are going to increase as we increase temperature. A catalyst is going to be something that will lower the energy required for activation of the reaction. So when we get to a catalyst, that is going to lower the EA requirement. So what you would see if a catalyst was present here is that this peak would be smaller relative to the reactants. It's going to lower the requirement because the catalyst is usually assisting in some chemical way with the reaction. So when the reaction is complete, the catalyst was not really consumed or used. It's not a reactant, it's simply assisting. So we expect to get our catalyst back. And again, when we relate this to biochemistry, if you're thinking about a catalyst, the enzyme that is responsible for binding to a substrate and turning out product, the enzyme is not typically consumed in that reaction. The enzyme is going to continuously interact with substrate until we saturate it and it can't work any faster. So that's how we can kind of relate enzymes to catalysts as a general chemistry term. So how do we mathematically relate these if we understand them theoretically? That is going to be done by using the Arrhenius equation. Now the Arrhenius equation will include temperature, it will include the energy of activation, and it will relate them back to the rate. So we know that rate is typically governed by the rate constant and the concentrations. So we find that the rate constant is equal to, and I will explain what each of these are, it's large A, E, and that E is going to represent the base natural log, and then exponentially we have negative energy of activation over RT. Alright, so what are all of these values that we've put into the Arrhenius equation here so we can see how they're going to affect the rate constant? T is temperature, and the temperature is going to be given in Kelvin. So Kelvin is the standard unit we use for temperature. We will oftentimes use Celsius, but Kelvin, because it has an absolute 0, is considered the standard for temperature in chemistry because we're dealing on an absolute scale. Now R comes from the gas constant, and the gas constant for this R is going to be 8.314. It is joules per Kelvin mole. That's a gas constant. So when we talk about collision theory, it is typically referred to with gas molecules because they have the fastest movement as they would be moving around in some sort of a reaction chamber. So R is used as a good predictor for the energy associated with these gas molecules as they would be colliding. We then have EA, which we've already defined above. This is going to be the activation energy for the reaction, or energy of activation, whichever you'd like to call it. All right, and then, as I said, the E is a mathematical term. It represents the base natural logarithm. So we were using natural logarithms earlier when we talked about ln. The E is basically the reverse of that, the complementary base natural log. And then A is usually a constant that tends to be given to students, or you're solving for it if you have a rate constant already, and that is the collision frequency. So how often are these molecules colliding, which we said is going to be important in determining the rate. So we would expect to see that's going to be built in. And you can see that temperature and the energy of activation both play a role in the collision frequency, and the collision frequency is going to directly or proportionally help determine the rate constant, how fast these reactions are able to go. So that is the Arrhenius equation and how we relate a catalyst, which is affecting the energy of activation, and temperature to the rate of a reaction. Now there is one other useful equation that is derived from the Arrhenius equation that I want to show here, and that is you can take the natural logarithm, so we're back to ln here, for a rate constant 1 over a rate constant 2. And you can set that equal to EA over R. And then you can relate those to temperatures, where T1, and you subtract that from T2, and then you have T1 times T2 right here. So this equation, if you have, especially if you have the rate constants, can be used to determine, let's say, the energy of activation. So I would like to find what the energy of activation for my reaction is going to be, provided I have measured two different rate laws, or I can compare the two, and I know the varying temperatures, then I can relate them back to EA here. All right, so that is a discussion on temperature and catalysts and how they would affect these reactions. So next up, we are going to take a look at enzyme kinetics, and when we are done with enzyme kinetics, we will then head into the practice. And again, I encourage you to keep a calculator nearby, because when we get to that practice session, it's going to be very math heavy with the number of equations we've been using. So let me clear the board, and we will be right back to talk about enzyme kinetics. Okay, so the last thing we need to discuss before we get ready for practice here is enzyme kinetics. So enzyme kinetics are going to be related to regular kinetics, as we would expect. However, there is some difference, particularly when you're dealing with a substrate. You can continue to increase the concentration, but it's only going to go so far. And then at a certain point, you will hit what's known as Vmax, which is where you're going to cap off the effectiveness of the enzyme because it cannot work any faster than it already is. So let's take a look at the general premise here. What you're going to have is an enzyme and a substrate. And the enzyme and substrate typically are in equilibrium with one another in order to form the enzyme-substrate complex. And that's what we have in the middle here. Now, after this point, it could either reverse back into the enzyme and substrate, respectively, or you could have a forward movement to the enzyme and product. All right? Now, what you need to keep in mind here that's going to be a little bit different than what we were originally looking at is you now have a potential for up to 4 rates, because you have rate 1, and rate 1 is going to be associated with the enzyme and substrate moving to the complex. You're also going to have rate -1, and that is the dissociation back to the enzyme and substrate. You then will have rate 2. Rate 2 is the dissociation of the enzyme and substrate into the enzyme and product, and then you could also have rate -2, and that is moving back in the direction where the enzyme and product would come back together to form the enzyme-substrate complex. So this is much more complicated than what we were originally looking at as far as general chemistry kinetics. Now, the rate of the complex formation, if I were to take a look at it, would be considered rate equals, and then when I want to do this, there is still going to be a K associated with it, and then I would have the enzyme and the substrate. So this is for rate 1, if I was moving over in order to form the enzyme-substrate complex. Okay, now you can have a rate of the forward dissociation, because keep in mind it could also go backwards if we dissociate it back to the enzyme and the substrate. Okay, so in order to get the rate of the forward dissociation, meaning we're moving over to the enzyme and product, then you're going to be talking about rate equals, you'd have your own K. This would be a separate K. It's a different rate. We're talking about rate 2 now. So it will have its own rate constant, and then the concentration would only be that of the enzyme substrate complex, because it is this moving over to this, right? So we would only have the concentration of the enzyme substrate complex to worry about if we're talking about the forward complex dissociation. Now, similar to when we were talking about collisions, we are going to need to talk about speed here. And the speed that's associated with this is going to be the speed at which an enzyme is able to push out a given product when it couples with the substrate. So enzymes have a limit to how fast they can work, and that's very important when we talk about the kinetics here. We never really capped off our kinetics when we were talking just about general chemistry and molecules that were at work. But when we get to enzymes, we have to consider this. So for instance, if I had, let's say, 3 enzymes, so I'll draw them as squares here, and each of these enzymes has a maximum capacity to work at 10 substrate molecules. They can turn over 10 substrate molecules in 1 second. Then the maximum work capacity that I have here, as far as the ability to produce product, would be that I could turn over 30 substrates in 1 second. So that would be per 1 second. I can't go higher than that. It's just like workers in a factory. You can't get them to produce any faster if you're already maxing them out. So the question is, will substrate increase the rate? Well, let's say that right now I'm only putting in, or the concentration is only providing about 2 substrate per second. Well, in that case, yes, I'm not utilizing these enzymes to their full factor because they can do up to 10 per second. But as soon as I hit that value, as soon as I hit 10 substrate per second, at that point, all of these are maxed. And so I cannot go above that. And at a certain point, what's going to happen is if I continue to increase the concentration of my substrate, it'll only be as good as I can approach the working capacity of the enzyme, and that is known as Vmax. That's a speed, and it's how quickly the enzymes can work. So in other words, once I hit Vmax, the way we're going to define Vmax is that the enzymes are going to be maxed with substrate. And if they're maxed with substrate, that means they cannot work any faster than they already are. So what is this going to look like if we take a look at it graphically speaking? So if I were to draw a graph, right, what I'm going to see is I can have the reaction rate. So this is V, how quickly can I move? And then what I'm going to have down here would be the concentration of substrate. So what I would see is that as I increase the amount of substrate, I'm going to rapidly climb in rate until at some point it's going to level off, right? And so the point, we would say probably like right here, because that looks like it's fairly straight and there's no continual climb at that point. So this point right here, when we've gotten straight, if we were to take it over to the rate associated right here, that's going to be Vmax. Because I'm continuing to increase the amount of substrate present and I'm getting no return as far as the output of product. It can't move any faster than it's already going. So this is a very important concept, that you level off and there is a Vmax, or a maximum capacity to turn over product from substrate. Now, many people, when they go through biochemistry, hear of something known as the Michaelis-Menten equation, and that is going to relate substrate to rate up until we hit Vmax. So some people have heard of Km, and Km, which is the Michaelis-Menten constant, similar to a rate constant, okay? But when we talk about this constant, it's actually a concentration at which you are half Vmax. So Km is going to be the concentration substrate at which Vmax is 1/2, or you could say half Vmax, whatever you want. Okay, so when we're at half Vmax, that means that we are currently working at half the capacity of the enzyme's ability to turn over the substrate into product. So if I could find where that is, I would look at, here's Vmax, so approximately half, okay, now we're eyeballing this, we don't have data, but approximately half of this, which is Km right here, whatever the substrate concentration is right here, that is Km. That's the constant. Right? Now there are some assumptions that we need to make when we're using this model, and we'll give the actual equation in a minute here. So first of all, it is going to assume that your K is constant. And when I say K, I'm not talking about Km, I'm talking about the rate constant associated with these up here. So these Ks remain constant. What did we say could affect K? We said temperature and additional enzymes or other enzymes could affect K. All right, so that means we need to be at a constant temperature, or the temperature is not having a significant effect on it. So the second thing that we also need to assume here is that the concentration of enzyme is going to be constant, because what we discussed here was that each enzyme can turn over a certain amount of substrate, and so if that's the case, if we have varying amounts of enzyme concentration that's present, our Vmax could potentially be changing all the time. It's going to need to stay steady as far as that's concerned. Now, something else that we talk about when we talk about assumptions with your kinetics for enzymes is something known as the steady state assumption. And what the steady state assumption states is that we are unlikely to have a dissociation of the, to have a reassociation of the enzyme product complex back to the substrate here. So when the enzyme and product are there, the enzyme substrate complex, the reverse or the rate -2, is almost non-existent. So that's known as the steady state assumption, that we will not have enzyme and product readily going back to the enzyme substrate complex. We can kind of ignore that when we are working with our kinetics. So that means that the dissociation is going to be rate 2. However, the association or the formation is only going to be rate 1 here. And the rate -1 would come back into play if this is an equilibrium for the dissociation. So you put all of that together, and what we're saying here is that if you look at that initial equation we had up there, rate 1 is going to be equal to rate 2 plus rate -1. So notice that the rate -2 is not here, and again, that's the steady state assumption, which is where we're saying we are not likely to have the product and enzyme combining back into an enzyme substrate complex. Once the product is delivered, it's pretty much done and we're set. So these assumptions, the enzyme concentration assumption, the steady state assumption that we won't have a reformation of the complex after product, and that temperature and any other type of factors are not going to be affecting the K constants, those are all required before we start utilizing the Michaelis-Menten equation. Now the equation itself is going to be rate, and rate will be shown often as V0. So we're talking about how quickly we are turning this over at some initial rate. And V0, that rate, is going to be equal to Vmax, which is the saturated point, times a given substrate concentration, over Km, which is a constant substrate concentration at half Vmax, plus the substrate concentration. So that is the Michaelis-Menten equation that we work with. So once you have this, you can utilize it, especially if you know your Vmax and your Km. It becomes very useful because then you can find the rate at any given substrate concentration. So if I know the maximum velocity or the quickest that the enzymes can move and turn over this substrate into product, and I do know the concentration at which I've achieved half of this, then what that leaves is I can utilize any concentration of substrate that I would like, and it will tell me the rate that I can expect as far as product turnover in return. So that is why this is a very useful equation. And a lot of times people talk about Vmax, Km. There's also something known as Kcat, and Kcat is referring to the constant for rate 2. So rate 2, just so you can go up and we can take a look at it, rate 2 is the enzyme substrate dissociating into enzyme and product. So Kcat, or the rate of catalysis, is how quickly we are moving the enzyme substrate over to the enzyme products. And so that would be Kcat if you ever come across that term or you see it used in an equation. So one of the equations that sometimes can be utilized is Kcat over Km. And what this is really referring to, if you use these two values, is your catalytic efficiency. And so it's telling you how effective you are at turning over those products based on the ratio of Kcat to Km. All right, so I will make sure that we utilize this equation. Because of time, we need to head into practice here, but I will put up a question where we can utilize the Michaelis-Menten equation just to test you and make sure you're okay with it. So we'll look forward to that in the next section. So that wraps up all of the material for enzyme kinetics and kinetics in general. So the next thing I'm going to do is bring up the questions here, and we'll do our normal walkthrough as usual. So let me clear the board and we'll take a look at that in just a minute here. Okay everyone, here are the questions that we are going to use to practice for general chemistry, kinetics, and enzyme kinetics. So the questions are as follows. We're going to start off easy and then work our way up in terms of difficulty with the math. The reaction shown here is, and you can see this rate with the rate law fully developed there. And the question is, what is the reaction order? So we're talking about the entire reaction, not just one of the reactants here. You have to take a pick out of those four. Number two, you can see there's a data table here similar to one of the ones that we've worked with. And it says, what is the order of the nitrogen oxide in the given reaction using the data provided? So if you take a look at the data that's in that table, and then you look at the nitrogen monoxide, you can see in that first column there that the concentration is held constant in trial 2 and 3, and then in trial 1 we see the variation. So that's going to be important along with the rates that are coupled with that to help answer this question. So the question here would be, what is the order of the nitrogen monoxide given the reaction and the data provided? Right? And then question 3 is going to relate back to the data found in question 2. So you're still going to want to utilize this table. And it says, given the data for the reaction in question 2, what is the rate constant? Remember, rate constant is K, so it's asking you to solve for the K associated with the reaction shown, and you can get that based on the rates and concentrations that are found in this data table. 4, a second order reaction has a rate constant of 7 times 10 to the 9th per molarity second. If the concentration of A is 0.068, what is the molarity of A 210 seconds later? So keep in mind, we're saying if the concentration of A is, and then we give that value, that is going to be A naught. So it's a starting concentration at some given time. And then it's asking what will the concentration be at 210 seconds after that, if we already know the rate constant. So what we're really solving for here is going to be A sub T, or concentration after a given amount of time has elapsed, and in this case the time is 210 seconds. So you're going to solve that. And then finally 5, we have an enzyme problem, just as I promised. So an enzyme has a Km of 0.7 millimolar. And at what substrate concentration will the velocity of the enzymes reach 1/4 of Vmax, given that Vmax is 100 millimoles per second? So you can see your options down there. Now, just a hint for this one, because I find students tend to get a little bit lost when they're trying to do the Michaelis-Menten. If you look at this, it's asking for V naught to be set at 1/4 Vmax. So keep that in mind. You're being given the actual value of Vmax. You know what it is in this problem here. It's given to you. So if it's saying that V naught is going to be 1/4 of Vmax, that's the V naught you're setting it to, you should be able to solve for the substrate concentration doing some algebra. Alright, so go ahead and try these. As usual, pause the video, and then you can unpause it when you're either done or you are ready for a walkthrough, and we will look at them together. Alright, so hopefully everybody had a chance to work on these. What we're going to do now is go through each one of them step by step. So number 1, the reaction shown here is, now this one was meant to be the simplest problem of the bunch. If you take a look, the nitrogen monoxide here is first order, and the chlorine gas would be second order. And so the way we find the order for the reaction overall is to sum the orders of all of the reactants. And so that is going to equal 3, and third order would be the proper answer in this case. So you can eliminate the others. And you can determine that just looking at the exponential multipliers here that are associated with the rate law. All right, number 2, what is the order of the nitrogen monoxide in the given reaction using the data provided. So you can see the data values here. We're going to start heading into some math when we work on this. Now, this one would be the easier of the two. Number 3 has a little bit more in terms of what you need to solve for. So here's what we're going to do. We're going to take a look at how this has changed as far as rate is concerned, where we have manipulated the two values for the nitrogen monoxide. So what I did when I solved for this is that I went ahead and I looked at the rate associated with the 10 times 10 to the minus 3 molarity of nitrogen monoxide. And then because 5 is where it changes in trial 1, so we've got this one and this one, you can see there's different concentrations here. Okay, so what I'm going to do is I'm also going to grab this rate. And if I look at the ratio of the change in rates here, I should be able to find out what's going on. And I need to frame that relative to the concentration change here. So what I will do is I will put 5.2 times 10 to the minus 5 divided by 1.3 times 10 to the minus 5. So what I'm doing here is I'm comparing the ratio of the rates. And if you were to plug that into a calculator, you would get the answer as 4. So what this is saying is that the rate has quadrupled when I have doubled the concentration. All right, so take a look at that. The rate has gone from 1.3 times 10 to the 5th up to 5.2 times 10 to the 5th. That's a times 4. That's a quadruple rate. And if I take a look at what happened at the concentration, 5 times 10 to the minus 3 goes to 10 times 10 to the minus 3. So this right here is a double in the concentration. So if my concentration doubled, right, so if NO doubled, meaning it went to 2, then the question is, how did I quadruple the rate? You would need this to be second order, because that would give you 4, right? So this is going to be the effect on the rate based on a doubling of the concentration. And so the answer here would be B. The order for the nitrogen oxide, we're doing a specific reactant this time, not the overall reaction, is going to be 2. It would be second order with respect to the nitrogen oxide. Right, now that's going to be important when we want to solve for 3. So given the data for the reaction in question 2, what is the rate constant? So remember, rate constant is K, and we can find K by setting it equal to rate divided by the concentrations raised to their respective orders. So you can really pick any of the trials that you would like here. I'll go ahead and I'll work with trial 2. So if you take a look here at the top of the screen, trial 2, let's switch colors here as we're doing this. So trial 2, right here, the values I want to grab are the value for the nitrogen monoxide, the value for the hydrogen gas in molarity, and the rate itself. So I'll start by putting the rate on top. So I would put 5.2 times 10 to the minus 5th. And this would be, you can see the rate at the, the rate units at the top of the table here. So that's molarity per second. And then if I take a look at this, on the bottom, I would have the nitrogen monoxide. That value is going to be 10.0 times 10 to the minus 3. Now keep in mind that this is going to be squared, right? Because we determined, as far as the rate order was concerned for the nitrogen monoxide, that it would be second order. And the hydrogen here, you would need to look at this and compare it, but you should be able, if you look at the data, to find out that it is first order. So you would need 2.0 times 10 to the minus 3, and you don't need to raise that to anything. That could say just how it is there. So if you found that out, you would go through and solve for this, and what you should find when you finish is 2.5 times 10 to the second, and the unit, you can see all the options have this, is going to be per molarity squared per second. Okay, I'm sorry, times second when you're looking at this. So the answer would be B in this case, and the other ones would drop out. So that's how you solve for that one. All right, number 4. A second order reaction has a rate constant of 7 times 10 to the 9th per molarity second. If the A, and we said this is going to be A naught, right? If A naught concentration at beginning time is 0.068 molarity, what is the molarity of A 210 seconds later from whatever that initial time was? So let's take a look at how we would solve this one. There's a key in the words here that you need to pick up on, and that's that it says a second order reaction. So if you remember, we had 2 different ways that we could solve for time relative to concentration, and those were using the various AT and A naught values in relation to time and rate constant. So because this is second order, the equation that we want to use is going to be the one that uses the inverse. So we'll want 1 over AT, and that's what we're going to solve for. We'll find the inverse and then we'll flip the value so that that value will equal the concentration of A at some time t, the time being 210 seconds after the initial. Then we have KT plus 1 over the concentration of A naught. And that's the initial one, that's the 0.068. So if I want to bring some values into this, what I'm going to do is set my 1 over AT equal to the following. All right, so we need to find the rate constant. That's given to us. It's 7.0 times 10 to the 9th per molarity second. All right, now the time, we're already in seconds, you can see by the unit, so 210 seconds. And then this is going to be plus 1 over the concentration of A naught, and A naught is 0.068 molarity. So this is what I need to solve for algebraically. If you plug that into your calculator, you should find that it equals 1.47 times 10 to the 12th. Now, remember, because some students would stop here, that this is the value for 1 over the concentration of A at time t. Because this is a reciprocal, we need to invert the value, and so AT can be set equal to 1 over 1.47 times 10 to the 12th. And that will take care of it. So if you solve for that, it's going to be a very small number. It turns out to be 6.8 times 10 to the minus 13th molarity. And so D is going to be the correct answer in this case. All right, some of these you might be able to get an easy guess, but a lot of them it's probably better to dive into the math when you're working on it. All right, 5. Now we're talking about the enzyme kinetics. So let's take a look here. For 5, an enzyme has a Km. Remember, that is Km is the Michaelis-Menten constant. That should be at a concentration. It's the concentration to achieve half Vmax, and sure enough, it's a concentration there. At what substrate concentration will the velocity of enzyme reach 1/4 of the Vmax given? That Vmax is 100 millimoles per second. So how do we set this up? We know the equation we're going to need is the Michaelis-Menten equation. So V naught is going to be equal to Vmax times the concentration of substrate that I'm interested in over Km, which is another substrate concentration at half Vmax, plus substrate concentration. So we know Km and Vmax. And it turns out we also know V naught, because if we read through this carefully, it says that V naught is going to be 1/4 of Vmax. That's what we're trying to find the value of as far as the substrate that's going to be associated with that, or the concentration of that substrate. So how do I set this up? Well, what I'm going to do is say V naught is going to be equal to 1/4 Vmax. If I know that Vmax is equal to 100 millimoles per second, then V naught must be equal to 25 millimoles per second. So now I have V naught. I know V max because that is up in the equation here, and I know Km. So I should be good to go as far as solving for my substrate concentration algebraically. So let's take a look at how that math is going to work out. We would say V naught, 25 millimole per second, is equal to, and then what are we going to set it equal to? V max, so V max is going to be 100 millimole per second, right, times the substrate concentration. That's what we're trying to find out here, right? We're looking for that. And then on the bottom is going to be 0.7, because that is what Km represents, and that would be millimolar plus substrate concentration. So I can solve for S in this case by doing some quick algebra and rearrangement. So if you work this through, you could divide through by 100 in order to clear the V max off of the right hand side. Now 25 divided by 100 over here, okay, is going to give us 1/4, and we know that that's what we were shooting for, was 1/4 of V max, right? So 1/4 is going to equal, now we just have substrate concentration, so that's a cleaner numerator, 0.7, right, plus substrate concentration. So this should be a lot easier for us to start solving. If we rearrange this again, we can set it up so that the equation reads 0.7 plus substrate concentration equals 4 substrate concentration, right? So in order to get rid of 1/4, we need to multiply both sides by 4, and then we can also take the denominator and move that around to the other side. So this equation now will be able to tell us what the substrate is going to be as far as concentration is concerned. So the way that we set that up is we would say 0.7 is going to equal, now keep in mind we need to, this is where this value is going to come from. We need to subtract S, right, from each side. So this would be a 1S here, because what I'm about to put is 0.7 equals 3S. So that's where that's coming from. We're algebraically rearranging this again. And then S is simply going to be 0.7 divided by 3. That's going to equal the concentration of S. And if you put that into your calculator, you should see that S is then going to equal approximately 0.23 millimolar. And if we go up and we look, that would be answer A as the correct answer. All right, so that is how you solve one of the Michaelis-Menten equations. Now, they could give you various things that they're asking you to solve for, whether it be Km or whether it be your Vmax or things like that. But this was an example where we could use the actual substrate concentration and pull that out from all the other known data. So what I will do is I will bring up the summary and we will discuss everything we went over and wrap up the video. So give me a second to clear this and I'll be right back. Okay everyone, here is our summary for what we learned in kinetics, and this was quite a long lecture, so there's a lot that we went over. First of all, we discussed general rates and how they're related to a change in time. So if you remember, we saw things where we were saying, such as delta concentration of B and then delta T. So the change in concentration of B relative to time, or sometimes it would be negative if it was the reactants. And so we have their reactants disappear because they get used up. That's a negative change over time. And then the products appear, so that's a positive change over time. We also noted that stoichiometric coefficients are important when we're looking at the rates. So if it's a 2-to-1 ratio, you need to put whatever had that 2 should have a 1/2 rate as far as its comparison to the other counterpart. Right? Rate laws, we went and looked at how to express these. They are expressing the reaction kinetics overall, and we said that the rate constant K can be experimentally determined by holding concentrations of some reactants constant and then looking and manipulating others and seeing how that affects the rate. We also looked at the order of reactants, and we had problem solving for both of these in the practice. Order of reactants is going to be how the concentration of A is going to affect the rate. So when we look at that, is it going to, for instance, quadruple the rate? Is it going to only double the rate? We can get that if we look at the order. So then when we see the overall order, that's just going to be the sum of all the reactants. And you can see I included in here a rate law. So it's a very general rate law that just says K and then A and B. But if you were to take a look at this, these are the concentrations, A and B, and then little a and little b are the order associated with each of those, and then K would be the rate constant. So keep in mind that concentration is related to time through the natural logarithmic ratio, and the concentrations at the initial time and final time with the rate constant. So this is when we did the ln's and when we were doing the inverse reciprocal plots for the second order like we saw in that practice problem. You are going to use these equations in order to relate time to change in concentration. So we started off basic when we were talking about it with general reactions, and then we are saying, okay, I start at some time x, I end at some time y. I want to know what the change in concentration is, or if I know the concentration change, maybe I want to know how long it's going to take for that change to occur, so I solve for time. Either of those can be done, and we relate them back to rate constant. All right, so these equations will change for first and second order reactions. We've discussed that, and now we've seen it. During our lecture, we saw an example involving a first order, and then we saw a second order example when we just went through and solved the practice problem. So you've been exposed to both of those. Half-life can be determined by simply substituting A02 in place of AT, because when you're looking at half-life, it's how long it has taken for exactly half of the initial concentration to decay. So the concentration at time t should be exactly half of the initial starting concentration. So that's a quick way to get at half-life when you're using those equations. The Arrhenius equation relates temperature and the energy of activation for a reaction to the rate constant. So we saw when we were looking at the collisions and how temperature can affect that, how a catalyst can lower the energy of activation, that those all tie back into rate constant, and we use that gas law constant in there as well. Temperature will increase the number of collisions. So when temperature increases, it will increase collisions. And that is because of the kinetic energy that is continuing to increase as we increase the temperature. A catalyst will lower the energy of activation requirements by interacting somehow with the reactants, perhaps making them oriented in a certain way so collisions are more likely. It's not always clear what the catalyst may be doing, but a catalyst does not participate. We will always get it back at the end of the reaction. Now, enzyme kinetics are related to enzyme turnover of a substrate as it produces product. A couple things to remember here. Reactions will have upper limits in this case, so we cannot just keep doubling the concentration of substrate over and over and over again and expect that Vmax doesn't have an upper ceiling. At some point, the enzymes will become saturated. They can't work any faster than they already are going, and that is our Vmax. It's as fast as the enzymes can move and produce. The concentration of a substrate can saturate the enzyme. That's exactly what Vmax is. Now remember, we're also assuming that enzyme concentration stays constant among other assumptions, such as the steady state assumption. Various substrate concentrations can be used to determine the effect on rate using the Michaelis-Menten equation. That's what we looked at in that fifth problem that we did when we were practicing. We said, okay, let's find the concentration of substrate that's going to return 1/4 of Vmax. If it returned 1/2 of Vmax, that concentration should be Km. All right. Now, Km is going to be equal to the substrate at half Vmax. So that's what we just mentioned there a moment ago. So that is it as far as kinetics is concerned. A lot of information. You want to make sure that you practice and you implement this, especially on the math side, because there can be a lot of equations that you have to work through when you're doing this. So other than that, I hope everybody found this informative, and that will wrap up the chemical and enzyme kinetics lecture. Thank you for learning with MCAT ACE, and we will see you guys for future lectures.